Hi, what I want to do for you today is do a hard problem in kinematics, one-dimensional kinematics, but it's got two objects and two phases. So this is a harder problem than you'd see on a test, but it's really good practice both for two-object problems and for multi-phase problems. So again, it's a little bit harder, but it's going to be really good practice for you. So the problem I'm going to do, a race driver has made a pit stop to refuel. After refueling, he leaves the pit area with an acceleration of 6 meters per second squared. After 4 seconds, he enters the main speedway. At the instant he enters the main speedway, another car passes him going a constant 70 meters per second. If the entering car maintains that same acceleration, how much time is required for him to catch up to the other car? So this is a pretty complex one. This is a good example of why we always start with a picture. So we've got the main racetrack, and then we've got a car coming in from the pit stop area. So here's my main racetrack, and I'm going to say this direction is positive. I guess I'll call, I don't know, this part my origin. We'll see. So I'll put my origin right here, and then I've got two different cars. So I'm going to say the first car, I'm going to call it A, is accelerating here to the main road, and then we've got B already moving on the main track when A comes in. All right, so what's going on? I think I have to do this very carefully because I have information from here to here when A is accelerating up to come into the track, and then I've got information from here where the two cars meet at the beginning to here where they end. So they're going to end at the same place. All right. So B is going to end here, still moving, and we're going to have A ending at the same place, and A is still moving. So how much time is required for A to catch up to B? So they're going to end at the same place. Catching up, passing, means they're at the same place. So I'm going to start, I think, I'm going to start here and figure out how fast is A going when it enters the main speedway. Because once I know that information, I should be able to figure out information for the ending point. So let's start with that one. Now, A speeding up, I guess I'll call it that. Doesn't matter what you call it. This is the A speeding up phase. So our 6 main variables: initial position, final position, initial velocity, final velocity, acceleration, and time. So how much do we know just for this initial part? We were told acceleration of 6 meters per second, and that's going to be positive because we're speeding up in a positive direction. And 4 seconds. Okay, we know that. I'm going to make an assumption that since this guy just refueled, that he's at a stop to start with. So starting from rest. Don't know how fast he's going when he hits the main speedway. X final, I don't know. But what I could do, I can have two different origins. For phase 1 here, I'm going to say this is my origin for this phase. So I'm going to have a little origin right here, and then I'll have a little X final right here when car A enters the main speedway. The only thing I can know is, okay, I set that there. Don't know how far that is. All we know is acceleration of 6, 4 seconds to enter. Okay, can I do anything with this? So we don't know X final. We don't know V final. And what do I want to know? Well, do I care how long it takes him to get up to speed and enter the main road? I don't think so. I could probably figure it out if I need to, but I think what I want to know is how fast is he going when he hits the speedway. So I think that what I'm looking for is V final. So X final, blank, we might need to figure it out, not necessarily. So here, my 3 equations that I typically use. I don't know X final, which means I can't use the long one, and I can't use the one with the delta X, the change in position, because I don't know the change in position. That only leaves me one equation. V final equals V initial plus AT. Will this work? Well, I'm looking for V final. This is my unknown. I know V initial. Do I know my acceleration? Yeah. Do I know my time? Yeah. Okay, this will work. Now that one is 0. I always like cutting out those zeros. Simplifies things. This is pretty easy. So V final is my acceleration, which is 6 meters per second squared, times my time, which is 4 seconds. So how fast is this guy going when he hits the speedway? 6 times 4, 24 meters per second. The unit looks good. Meters per second is velocity, and 24 meters per second, that's about 50 miles an hour. I think that's a reasonable number. Okay, so now we know that car A is going 50 miles an hour when they enter the speedway. So A is 24 meters per second coming in. How fast was B going? So B was going 70 meters per second. Oh boy, gonna take some time to catch up to that one. And the question we're asked is, how much time is required to catch up? So we want to know how much time it takes to go from here to here. That's what we want to know. All right, so we're done with phase 1, but now we have to go to phase 2, and now we have 2 objects. So with a 2-object problem, what we want to do is have 2 charts of our kinematic variables. So we'll have one for car A, we'll have one for car B. So I'm going to get rid of that from the first part, and then all I need to do is add a second one for car B. Same 6 variables, those don't change. So initial position, final position, initial velocity, final velocity, acceleration, time. Okay, what do I know now? And now keep in mind, we're no longer here to here. This is my new time start, and this is my new time to finish. So I have a new origin here. Well, it says the moment he enters the speedway, another car passes him going a constant 70. I'm going to say that they both start at my origin then. So we've got a 0 there. I've got initial position 0 here. And do I know x final? Do I know how far they've gone? Nope. Do I know A? Initial velocity of A. I do know that. That was the thing I just figured out. Okay, so that's 24 meters per second. Do I know how fast it's going here? Do I know its acceleration? Well, we're told it maintains its acceleration, so this is going to be the same as before. 6 meters per second squared. And time, I don't know time, that's what I'm looking for. So this is my question mark. How about for B? Initial, okay, we don't know that, but we do know how fast it's going. 70 meters per second. We don't know how fast it's going at the end. Or do we? Constant 70 meters per second. So B has cruise control on at 70 meters per second. That means it's not changing. Final, initial, both the same. 70 meters per second, 70 meters per second. That means I know my acceleration too. If there is no change in velocity, there's no acceleration. So I know 3 things just by those 2 words, constant 70. Pretty good. So I don't know that, and again, time is what we're looking for. Okay, I got my picture, I got my chart, so now we need to figure out how to get the time. Now with 2-object problems, one of the things you have to do is realize what's going to be the same between these 2 charts. Because that's the key to solving these. You have to realize, oh, wait a minute, there's relationships between the 2 objects. So in this case, they end at the same place, which means x final here is equal to x final here. So these 2 are equal to each other. All right, so I know that. I also know that the times are equal because they started at the same time here. They're ending at the same time when it catches up to B. Okay, so my times are equal, my positions are equal, and I want to know what the time is. At this point, you might say, well, maybe I can just solve it with one chart or the other. Constant velocity is usually easiest, no acceleration. I don't know how far we're going. So if you're doing 70 and you don't know how far you're going, you're not going to be able to get the time. How about this one? All right, and again, same thing. I know how fast I'm accelerating. I know how fast I started. Don't know how far I'm going, so I can't get the time. So if I can't get it from A, can't get it from B, what do we do? Again, go back to the relationships. How do A and B relate? So in this case, we know that the positions are equal. The final positions are equal. So x final for car A is the same as x final for car B. I have equations for x final. So I can use equations to say, well, maybe I can figure out what this is. X final is equal to X initial plus V initial times the time plus 1/2 acceleration time squared. Same thing over here. X final is equal to X initial plus V initial time plus 1/2 acceleration time squared. So you'll note I'm putting A. All these are for A because that's the X final for car A. Same thing over here. B, all for B. Now the reason I don't have to put TA over here and TB over here, there's only one time. Times are equal. So I can say that this time over here for A and this time over here for B are the same. Okay, that looks messy. 6 terms. Again, I always like to get rid of anything that's 0. Simplify by figuring out what's 0. X initial for A is 0. Gone. X initial for B is 0. That one's gone too. Anything else 0? Oh, I've got another 0 there. Acceleration for B is 0. Acceleration for B is 0. All right. So from 6 terms, I've cut out 3. I'm down to 3 terms. Let's rewrite that. B initial A times time plus 1/2 acceleration of A t squared equals V initial B times time. Okay, that doesn't look too terrible. What am I trying to find? I always go back. It's like every once in a while you've got to remind yourself, what am I looking for? I'm looking for my time. Can I solve time with this? Do I know V initial A? Yep, I'm looking for time. I know 1/2. I know the acceleration of A. I'm looking for time. I know V initial B, and I'm looking for time. Got it. The only unknown in this equation is time. So this will work for me. At this point, the physics is more or less done. We're just going to focus on getting those numbers in and seeing if we get a reasonable answer. So let's do that. What kind of numbers do we have? V initial A. Okay, 24t plus 1/2, the acceleration of A was 6, t squared equals V initial B, that one, 70t. You might stop and say, uh-oh, this might be a quadratic. You know, I'm seeing a t squared here and a t here. We're going to be okay because we don't have a non-t term. It'll be okay, no quadratic. Let's go 1/2 of 6, 3t squared. Let's bring that 24 over to the other side. So it's going to be 70 minus 24, t on this side. And take a look, I've got a t squared here and a t here. I'm going to cut out one of those t's. Divide both sides by t. Gone, gone. And then this one over here cancels that one there, leaving me 3t over here equals, well, 70 minus 24 is going to be 50, 46. Okay. Almost there. Almost there. So at this point, 46 divided by 3 is going to be 15 and 1/3. 15 and 1/3 seconds. Okay. And again, don't stop and just move on to the next problem. You always have to say, did I answer the question? Is it reasonable? Check what you're doing before you walk away. So 15 seconds. Is that a reasonable amount of time for car A to catch up to car B? We started out at 24 meters per second. Well, we got to go all the way up to 70, so it is going to take some time. 15 seconds, that seems quite reasonable to me. So I think that we've answered the question. Now we have something that we can use to check our answer. And one of the nice things about two object problems is that you've got this built-in check. I have an equation for where x is at the end. I have an equation for where B is, or sorry, where A is, for where B is. They better be the same. So now that I know my time, I can put that time into this equation, see where A ended up. I can put my time into this equation, see where B ended up. If they're the same, we probably did it right. If they're different, we know we did it wrong. Can't be guaranteed we're right, but you definitely know when you get it wrong. So our time was 15 and 1/3 seconds. I'm going to write that down before I erase it. Let's see where A and B end up. So I've got, oh, I'm erasing the wrong thing. That's okay. I know what the equation is. You have it in your notes. It'll be okay. And now we've got the time. We've got all of these variables. I think we've got everything we need. So let's figure out how far these cars go. And you know, you might stop and say, can I estimate it? How far do I think the cars would go? Well, I'm not sure. Well, it's going to be probably a long ways. If I get 5 meters, I know I did something wrong. If I get 50,000 meters, I know I did something wrong. So, I don't know, 1,000 meters, maybe? Something like that. So let's try A. So x initial was 0 plus v initial t, so 24t, 15 1/3, plus 1/2 the acceleration, times t squared, 15 1/3 squared. That's on the A side. The B side, we have x initial, which is 0, plus v initial t, so 70 times time, plus 1/2 a t squared. That term dropped out. So if we do the math, that one's easier. I'm going to start with that one. So this one, 70 times 15 1/3, I get 1073 meters. Okay, let's hope we get the same thing with A. So if I do the math here and do that one, I get 1073 meters. Okay, pretty good sign that we got it right. And it's totally reasonable. 1,000 meters, 1 kilometer, you know, 0.6 of a mile to catch up. Definitely in the realm of reasonable. So I would say we did this one right. Everything's reasonable. We've answered the question. We're in great shape. So the last thing I want to do with this one is the graphs, the 3 motion graphs, position, velocity, acceleration, for A and B. And I'm going to put them on the same set of axes so that I can see how they compare to each other. Because if I did them on separate axes, it wouldn't be easy to compare, you know, if they had different slopes or something like that. So I'm going to say let's do the same set of axes, position and velocity and acceleration. Okay, so there are my 3 motion graphs. I always start with acceleration. If we're using these equations, A has to be a constant. A has to be a flat line, constant acceleration. So, acceleration of A. I got too many A's here. So the acceleration of A, car A, is 6 meters per second squared. And here I should mention I'm only going to graph this part. I'm not going to worry about that picking up speed part. That's just the first car. So I'm going to do this part right here. So the acceleration of A was constant 6 meters. Okay. So car A, constant at 6 meters. The acceleration of B, oh, that's kind of boring, but okay. So we're just hanging out at 0. B is hanging out at 0, no acceleration. Both are flat, constant acceleration. So that's the easiest. This is going to be next easiest. And I can use my information from my charts. So for car A, we start at 24 meters per second. 24. Okay, so A starts at 24. We don't know what the number is for V final, but we know that it has a constant acceleration, positive acceleration. Constant positive acceleration means a constant positive slope here. So, whoop, it's going to keep getting bigger. And that should make sense physically. They're going to keep on picking up speed in the positive direction, get faster and faster and faster. All right, and then for car B, we're moving at a constant 70 meters per second. That's kind of boring. Cruise control is on, and we're just hanging out at 70. So here's car B, here's car A. And now you might say, where do they meet? Do they have the same position here? If you start out at 24 meters per second and somebody blows by you doing 70, if you speed up to 70, have you caught them? Of course not. You have to go faster than them to catch up with them. So this is not the point where they meet. This is not where A passes B. That's going to be over here. A is going to have to be going faster than B, otherwise they'll never catch up. So now the hard one, position. Remember, if there is acceleration, position needs to be a curve. So for A, we have to have a curve on this graph. For B, there's no acceleration. No acceleration, this would be a flat line. I'm going to guess this is an angled line. So A, we start at 0, okay? And we ended at 1073, so we know the ending is at 1073 meters. How does A get there? We started with a small velocity, and the velocity gets bigger and bigger positive. So small velocity, so we have a small positive slope, and that positive slope is getting bigger and bigger and bigger. Okay, a little bit sloppy on the front. It's not flat to start. We start with some initial velocity, so it's not perfectly flat. Now B is going just a constant 70, and they start at 0 as well. So B is starting right there, and if they go to constant 70 meters per second, well, that's just going to be a straight line going up. So a constant velocity means a constant slope. So B is going to be straight line, and A is going to be a curve. And now this point really is where they meet. So that is the, what was it, 15 1/3 seconds. And okay, not to scale, not to scale. That's going to go across to 1073 meters. This should take care of everything. Constant acceleration for A, 0 acceleration for B. B is just moving 70 meters per second, boring. A is speeding up from 24, and then B just a nice smooth going up 70 meters per second. A is speeding up, 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 up. I think we've got these all taken care of. We've answered the question. We've done all 3 motion graphs showing where they are and what the relationship is between the two. I think we got it. Good job.